Any more homework assignments for 2B? 2B or not 2B? That is the question. All right. We're going to have a lab today, and so I asked you to grab a copy of the lab handout along with the class notes. We're going to have Group B meet at 2 o'clock and Group A meeting at 3 o'clock. Please don't be late for lab or for class. The lab assignment from last time is due at the beginning of your lab group, and then you'll have 1 week to complete the hydrostatic lab. I've changed the handout a little bit compared to previous semesters, so for the lab handout I did my best to make it a little bit more understandable than it has been in the past, but I'm sure I'll probably make changes again next year. So let me know if you've got questions about the lab procedure. You know, we'll have a chance to talk about it at the beginning of our lab today. Homework 3A is due a week from today. We're going to be talking about hydrostatics today, a continuation of our earlier discussion. And just to refresh your memory about the hydrostatic equation, consider this tank that's 50 meters tall, and we know the pressure at 1 is equal to the pressure of the air that's in contact with that liquid surface. And so does anybody know what is the absolute pressure at sea level of the atmosphere in pascals? So what is standard atmospheric pressure? What's that? In pascals. So I think you maybe are thinking in terms of PSI. In pascals, it is 101,325 pascals. And a pascal is a Newton per meter squared. So I'd like, just so you can remember both forms of the hydrostatic equation that are introduced in class last Thursday, try and find out what is the pressure at location 2 and use both methods. Use the full hydrostatic equation and then also use just the delta P approach to find the pressure at 2. And we want to know the absolute pressure and the gauge pressure. So I'll give you a couple minutes to get started on that, and then I'll begin working the solution on the board. We're asked to solve this problem 2 different ways and to find both the absolute and the gauge pressure according to each method. In the first approach, we're using the full hydrostatic equation, which says that you have a constant sum of elevation and pressure head as you move through the fluid from 1 to 2. So we're going to take location 1 to mean the top of the tank where air is in contact with the liquid, and 2 is this submerged location 35 meters beneath the surface, or the other way of looking at it is that it's 15 meters above our vertical datum. So let P1, if we're trying to find what is the pressure at 2 in absolute terms, absolute means that we are assuming the atmosphere is over and above vacuum. We're not letting the atmosphere equal 0. We're keeping track of the actual pressure of the atmosphere for absolute pressure. So P1 is 101,325 newtons per meter squared, which is the standard atmospheric pressure. We solve the hydrostatic equation for P2 and substitute in all the known values and find that the pressure at 2 in terms of absolute is 444,675 newtons per meter squared. So that is how much pressure there is at 2 relative to a vacuum where there's no pressure. But if we wanted to express the pressure at 2 in terms of gauge, what you do is you subtract the atmospheric pressure from the absolute. So you're saying let 1 equals 0, in other words. If we worked this whole problem over again from the top, in terms of gauge, we just say let P1 equals 0. And so where you're subtracting out atmospheric pressure, the gauge pressure at 2 is 343,350 newtons per meter squared. So that's the full hydrostatic equation. When we solve it in terms of the abbreviated hydrostatic equation, which is just tracking the change in pressure through a fluid, remember that pressure goes up when elevation goes down. So it's the opposite direction, and the rate of pressure increase is equal to the unit weight, gamma, for this liquid in question, which is water here. And so the increase in pressure is going to be equal to the delta H of 35 meters times the unit weight of water, 9810 newtons per meter cubed. And you'll get an increase of pressure of 343, 350. That should look familiar to us because we found the change in pressure was the same thing according to the full hydrostatic equation. So that if we want to know the absolute pressure at 2, we have to add the pressure of the atmosphere at the top as our starting point plus the change. And the change is added because as we go down through a fluid, the pressure increases. And then if we want to find the gauge pressure, it's simply set the pressure at 1 equal to 0. So then the pressure at 2 is equal the same as the change in pressure. Did everybody get a copy of the notes, by the way? And a copy of today's lab handout? Any questions? Mm-hmm. Well, in this approach, what we're doing is we have Z1, so the elevation at 1 is, we're letting this bottom of the tank be our elevation datum. And so location 1 has 35 meters of elevation and location 2 has 15. And so I actually substituted in the actual elevation of 50 and 15 because this is all on the basis of elevation above the datum. But in the second method is where I use the 35. I don't know if that answers your question. Yeah. Okay, all right. Other questions for this example? What if we had 2 different liquids? We've got oil on top and water down beneath. By the way, on the quiz, it seemed like some people understood specific gravity and some people were still struggling with that concept. So let's say if this is a specific gravity of 0.75 for the oil, how can we find the density of that oil? If Sg is 0.75, what does that mean about the oil? What is the density of the oil? Anybody remember what's the definition of specific gravity? All right, so specific gravity is the density of some liquid relative to the density of water. And anytime the specific gravity is less than 1, that means the liquid is less dense than water and it'll float on top. That's why we see that the blue layer is meant to represent water and the brownish, yellowish layer is meant to represent the oil. So in our case, if the density of the oil is desired, we say it's 0.75 times the density of water, which is 1,000 kilograms per cubic meter. So just by looking at it, by inspection, we should instantly say, oh, this oil has a density of 750 kilograms per cubic meter. Now it's not that straightforward when we want to find the unit weight, and in this case it's actually the unit weight that's a little more relevant because that's the factor that we use in finding pressure changes. But all we have to say is that the oil unit weight is 0.75 times the unit weight for water. And so the unit weight of the oil is 7357.5 newtons per meter cubed. Okay, so we've got water is 9810. This oil is 7357. And the description of the dimensions are a little bit tricky. You've got a homework problem that looks almost identical to this in terms of trying to find pressure at certain depths into here. They say the total liquid level is 4 meters. So that means it's 4 meters to the bottom of the tank of the liquid up to the very top. So 4 meters total. And the oil is 1.1 meters is the thickness of the oil. Okay, so how thick is the water layer then? 2.9, right. That's the thickness of the water layer. Okay. So we want to find the gauge pressure at the bottom of the tank. Here's the hydrostatic equation. What would be the problem, do you think, if I said, here's location 1, here's location 2, let's just apply the hydrostatic equation in a single step? What would be the flaw with that approach? There is a flaw. What do you think? It's 2 different liquids. Yeah, we can set the elevation at 2 as 0. That's fine. That's not a problem. If we say that the bottom is our z datum, so according to here, we'd have let z2 equal 0. But we've got 2 different liquids. So what? I mean, can you go into a little bit more detail of why that might be a problem? That is the problem, but why? Okay? And what do you mean? Well, if this tank is, I need to maybe raise the screen a little bit. This tank is open to the atmosphere. And so here's the air, and we're finding it in gauge terms. And so we're saying basically let P1 equals 0. So actually that is known just sort of by the fact that these walls go up the side and it doesn't look like there's a top here. We're assuming that that's vented to the atmosphere. I could put these little triangles to make it even more explicit. And there's little ripples to even emphasize it further.
The pressure on the water is not air pressure.
Okay, the pressure on the water isn't the same as air pressure. So the pressure accumulated, and then it accumulated at a different rate. If we were going to graph the pressure, this oil is less dense than the water. And remember, what unit weight is the rate of pressure increase. So what if I drew a graph, and here is depth, and then here is pressure. So what it would show is that the pressure increases slowly as we go through the oil, and then the pressure increases more quickly as we go through the water. So there's 2 different rates here because there's 2 different liquids. You can only apply the hydrostatic equation through a single liquid at a time. And so what we have to do is we have to say, here's one at the top where you've got the air-oil interface. Location 2 will be the oil-water interface. And then we're going to make this location 3 where it's the bottom of the tank. And so the approach that we'd need to solve is, okay, we've got the oil unit weight, and we're going to let P1 equal 0. So P1 is equal to 0. P2 is going to equal P1 plus delta P from 1 to 2. Okay? So that is going to be 0 plus gamma H times the unit weight. Delta H times gamma. So that's 0 plus 1.1 meter through the oil, which was 7357.5 newtons per meter cubed. Okay, so that tells us that the pressure at 2 is 8093.25 newtons per meter squared, and that's a gauge pressure. What do I mean when I'm writing gauge in parentheses here? Okay, so it's not absolute. It's saying this is the pressure where the atmospheric is the starting point. It's let atmospheric pressure equal 0. So that's the pressure at 2, and then pressure at 3 is P2 plus delta P from 2 until 3. So that is the 8093.25 newtons per meter squared, plus we're going down 2.9 meters into the water, and water has a unit weight of 9810 newtons per meter cubed. Okay, so this increase here, that increase is 28,449 newtons per meter squared. And so the total pressure at 3 is going to be 36,542 newtons per meter squared. So however many layers there are, you have to break that up into steps. If you had an oil layer, a water layer, and then a mercury layer, and you wanted to find the pressure at the bottom, you'd go through one fluid, stop, find the pressure at the interface. Then you go through the next fluid, stop, find the pressure at the interface, and then go through the third. And you have to break it up into as many steps as you've got different types of liquid. And the reason why is that each liquid is going to have its own different unit weight. So this unit weight only applies through a continual fluid. You can go straight up and down, but only through one fluid to have it apply. Does that make sense? Yeah.
So if we use the absolute pressure instead of gauge pressure with 0.1, that just be the atmospheric pressure?
Exactly. So if we wanted to find, instead of the gauge pressure, if we wanted to find the absolute, then we would start with 1 equaling 101,325. That's right. And sometimes we accidentally mix up atmospheric and absolute. And what makes it even more confusing is that the two are related. Absolute pressure is where you are including atmospheric in the calculations. Gauge is where atmospheric is set to 0. All right, so you should be able to jump right into the homework assignment, the next one, without delay. So this is one of my favorite diagrams in the book because it introduces one of the most counterintuitive ideas, and that is pressure transmission. One of the things that pressure can be very useful for is lifting heavy objects like cars. So here we have a compressor. It's not pictured, but at the end of this tube is a compressor. And if you want to lift this car, you turn on the compressor, and what the compressor does is it pumps additional air in here that pushes down on the oil, and that downward force, that downward pressure on the oil pushes up against this cylinder, and then it basically will lift the car. And the formula that actually describes how heavy that car can be is very simple, and that is that a force is pressure times area. So just to illustrate pressure transmission and how you can find the hydrostatic force from a hydrostatic pressure, let's consider that we have this cylinder here. If this is a big steel cylinder that has a diameter of 25 centimeters, we can calculate the cross-sectional area from that according to the formula. Area is pi d squared divided by 4. So I've just already done that for you. I've given you the area. What if the pressure inside of this tank is 600 kilonewtons per square meter? What does that tell us about how heavy the car is? So we can calculate that just by pressure times area to find the weight of the car. Because the weight of the car and the upward force that the pressure exerts on the cylinder are going to be equal to each other. So the force is pressure times area, and so that is 600,000 newtons per meter squared, and the cross-sectional area of that cylinder is 0.04909 square meters. That's 29,454 newtons. That's the weight of the car, and that corresponds to a mass of about 3,000 kilograms. Pretty heavy. 3 metric tons. So that's a heavy car. Maybe it's like a Mercedes or something. They're usually pretty heavy. Pressure times area. So what would happen if we turn the compressor on? If we add more air, why is the car going to go up if we increase the pressure here? Why would that make that rise if we added more pressure? No, the area stays the same. The area that we're talking about is like the bottom circular area of that cylinder. If we put more air in here, if we turn on the compressor, that's going to make this rise. And eventually it'll rise and then it'll stop if we add more pressure in there. Why does it rise? What's that? The oil's incompressible. Okay, that is true. But why does that make the cylinder rise?
The air is less dense than the hydraulic oil?
Well, the air, yeah, that's also true. Is the air is less dense. Let me draw what it's going to look like when we add more air to there and it displaces the oil. Yeah, it is sort of like an equilibrium situation. We're in equilibrium right now, as pictured, with it being 600 kPa. So if we put more pressure, it's temporarily not in equilibrium. So it's in equilibrium right now. Right now, you've got the weight of the car plus cylinder acting down, and then you've got this pressure increases a little bit as you go through the oil, because anytime you go down through the fluid, the pressure is increasing. And then as you go sideways, nothing happens, right? But then when you go up, the pressure is decreasing. Now these are about the same elevation. So the pressure here is going to be the same as the pressure acting up. So here's our pressure, and then the area that it's talking about is that cylinder's the bottom area of the cylinder. And so the force that's acting up, the force due to this pressurized oil, is pressure times the area. So what we have in equilibrium is that the weight acting downward is equal to the force that's applied by the pressurized oil. So if we put in more air, that makes the pressure higher. So I'm going to make these lines longer just to indicate that the pressure is higher. And so what that does is it causes the cylinder to rise. So maybe now the cylinder would be up here, and this is all oil. It would, the weight doesn't change, right? The weight of the car and the weight of that steel cylinder, that's not affected by how much air we put in there. And so W is going to be the same, but the way that we cause it to rise is that, remember, the pressure is decreasing as we go through the oil. And that's really the key to why it rises, is that we have increased the pressure so that the extra amount of pressure we added causes an additional deflection of this lift, and so the incremental increase in height is just equal to delta H is, if you remember, pressure is delta H times gamma. We can find the delta H by being the change in pressure divided by the unit weight of the fluid. So this oil has some unit weight. If we increase the pressure, then that's going to cause this to go up or down. If we decrease the pressure according to just the hydrostatic equation. So if we open up this control valve at the top and we let pressure out, if we let out air pressure, then the air won't be pushing on the oil and the oil won't be pushing on the cylinder. It's very counterintuitive. We can lift heavy things by either having a big pressure or a big area. Because remember that the force is pressure times area. So you can lift something heavy like this either by having a big pressure or a big area. So it seems really weird, but if we had a larger cylinder with a larger area, then we wouldn't have to pressurize the oil as much as we did with that small cylinder. And that's going to be illustrated with another example here in a second. The book does a really good job describing this, and I'd encourage you, if you're struggling with the concepts associated with this, to spend some time reading through the textbook. Okay, this illustrates that pressure transmission issue maybe even better than the previous example did. Now think about this part and what it does. When you push down on the handle, first of all, we've got a moment analysis that we have to do. It's acting about a hinge at location C, and so if you press down on the handle, then this plunger is going to be pushing down on the fluid inside of the jack, and the fluid is resisting that, so it's pushing upwards at B. And so in this example where we're going to try and find out how much can the jack actually lift if you are applying a force of 100 newtons. So if you're pushing down at 1 with 100 newtons, how much can it lift at 2? One of the things we're going to have to do is a moment analysis, and so this jack is sort of amplifying the force that it can lift, first of all, by the fact that you're pushing really far away from the pivot point, but the pivot point is pushing back, but the force is resisting that close to the pivot point. And so with your greater moment length, you're able to amplify the force. So when you push down, it pressurizes that fluid, and then it's pushing up on the jack cylinder. And you'll notice that these two areas aren't the same, that this area is bigger, and by having this area larger, you're able to lift something heavier. So let's go through these calculations, and maybe this will make additional sense as we do. We want to find out what load can it actually support if we've got a 100 newtons that's being applied at 1. Okay, so we start off with the handle, and 100 newtons is being applied 33 centimeters away from this point about which it pivots. Okay, so 33 centimeters, and then this force, I'm going to call it force B, is only 3 centimeters from the edge. Okay, so we know that the counterclockwise moment is 100 newtons acting at a distance of 33 centimeters, and that's going to be counterbalanced in equilibrium by whatever that force at B is, which acts at a distance of 3 centimeters. when we're pushing down on it and the force up on that bar is resisting it, the force at B in equilibrium is going to be 1100 newtons. So this is just how much the force at B is when we're pushing down and they're balancing out. So I'm going to write at equilibrium when the forces are balanced, when the moments are balanced, really. So what's the pressure of oil inside of this hydraulic jack? We can find the pressure of oil inside the hydraulic jack if we calculate the area that that force is being applied to, because we've got this little sort of device that it is pressing down with FB. So it's 1100 newtons is acting downward, and here it's got some cross-sectional area, and what's pressurizing the fluid is the force that's being applied and the area over which it is being applied. So the pressure of the fluid will be the force that's applied and the area that it's being applied over, which is here area 1. Okay, so it is 1100 newtons, and the area that it's being applied over is pi d squared, where the diameter is going to be 0.015 meters, divided by 4. This will tell us how much pressure is inside the hydraulic fluid at the interface. And remember, the pressure will increase as we go down through the jack. I'm talking about the pressure right where that force is being transmitted into the fluid. At the interface of that steel cylinder that's pushing on the fluid and the fluid itself. Okay, so this area, if we calculate the pi d squared divided by 4, that area is 0.0001773 meters squared. And the pressure is 6,225,000 newtons per meter squared. 6 million megapascals. We better have a pretty good, a nice, strong cylinder. I bought a log splitter from Harbor Freight. So everybody starts laughing, right? Harbor Freight is where you go to buy junky tools. And I bought a hand crank log splitter, and it splits some big logs. Like, I've split probably like 24-inch diameter logs with it, and it says in the instructions not to split anything over 6 inches. But I've got the strength, obviously, to split big logs, but this thing is constantly leaking fluid. I have to always be pouring in more and more hydraulic fluid, because I think probably why they said not to put more than 6-inch diameter logs is you need so much force to split the big logs apart that whatever seal they have in the jack, because this log splitter is actually just a jack like this. You're pressing on the jack and it's pushing this log into a wedge to split the log in half. But I must be developing it's got a long handle on it, like this does. The longer the handle, the easier it is for you to create a pressure inside the jack. But here, 6 million megapascals, that's going to be a lot of pressure. And an ordinary hose, or just a fitting that you maybe clamped with a screwdriver and one of those wire rings that goes around like a ordinary low pressure fitting, isn't going to work so well. Okay, so here the oil pressure is 6 million megapascals. As we go down, the pressure will increase a little bit. How does the pressure change as we go sideways through a fluid? It's the same, right? Pressure only changes when you're moving vertically through the fluid. So go down through the pressure increases a little. Sideways, it's not changing at all. Now, it's probably not changing a lot because how big is the jack? You know, a jack would maybe be a couple of inches. And so when you've got 6 million megapascals, you probably wouldn't even be able to measure the pressure increase as you go down a couple of inches and up a couple of inches. It's going to be irrelevant relative to the rest of the pressure. But the main point is that both of these are at the same elevation. Both the surface A1 and the surface A2 are at the same elevation, and so the pressure is going to be the same at both of those locations. So now I want to find out what is the force acting upward, and I'm going to use the pressure that's acting on surface A2 in order to do that. Okay, so we know that the pressure acting at location A2 is 6,225,000 newtons per meter squared, and then the area at 2 is going to be pi d squared, where it's 5 centimeters, so the diameter is 0.05 meters squared divided by 4. So area 2 is 0.019635 square meters. The upward force that it's adding to that lifter is going to be the pressure times the area. And so that is the 6.225 times 10 to the 6th newtons per meter squared. And then multiplied by the area, which is 0.019635 meters squared. So, yeah, that's right. It's going to be the upward force that's acting on the lifter, and that'll be in equilibrium with F2. And so F2 is 12,222 newtons. So that's why I can split a 12-inch, I can split a 24-inch log just by pushing back and forth on the hydraulic jack, and I'm not even having to press that hard. Is because, number one, my force is being amplified by the long moment arm of the handle. That's a big part of how you get that big force. But then it also is amplifying my force by the ratio of the areas. So if you have a doubling in the areas, that doubles the force. If you have 10 times the area, then that multiplies the force by a factor of 10. So in this case, we push down with 100 newtons, and we can lift 12,000 newtons. Any questions about that concept? That kind of, I remember when I started teaching fluid mechanics, I started teaching fluid mechanics in the fall of 2005. So this is my 10th year of teaching at the university level, and it had been a while since I took fluid mechanics to when I was teaching it, because I took, as a student, fluid mechanics, I think, in the 90s, the late 90s. And so I had to reteach myself a lot of these concepts, and this blew my mind, that the idea that different areas can allow you to lift something heavy, that was like one of those things that had me a little bit like stunned for a while. Took me some time to wrap my head around it, but the homework will help you wrap your head around it, yeah?
So if the pressure at A1 and A2 wasn't associated, would we have to figure out exactly what the pressure is?
Okay, so the pressure, both of the pressures are the same. The pressures are the same. Okay, so let's say they were at different heights. What if, that's a good question, and we do have the time to take a look at this. So let's consider what if they weren't the same? You know, what if the pressure here is that 6,225 pascals, and then what if it was oil all the way up here and it was like 1 meter higher. So a meter's a lot. So 3 feet. What if there was a 3-foot deflection? So the delta P for 1 meter is going to be delta H times the unit weight of the oil. Well, we don't know what kind of oil this is, but it couldn't be, since it's oil, it won't be more dense than water. So, worst case scenario is it's going to have something close to the unit weight of water. So it's going to be 1 meter times maybe 9,800 newtons per meter cubed. And so the delta P is going to be in the order of 9,800 newtons per meter squared. And so 9.8 kilonewtons out of 6.2 meganewtons. It's going to be, a very small pressure change. And so it probably wouldn't even be measurable even if it was a meter elevation difference. But in this example, since they're by inspection, we can tell that they're at the same elevation. We don't even have to worry about the difference in pressure acting on one versus acting on two. One of the ways that we can measure pressure is with something called a piezometer. And think about water flowing through a pipe, and if we just punctured a hole in the pipe, water would be spraying everywhere. And maybe you've done that before, like maybe you accidentally hit a water line. That's a lot more common out in the West where people have to irrigate their lawns in order for them to stay green. People will have these PVC pipes going all through their yard, and there will be sprinkler heads at different spots in the yard. And so inevitably, like when I was a little kid, I did Scouts, Boy Scouts, and we had this fundraiser where we would put up flags in people's yards. And so every 4th of July, somebody would put the flag in someone's yard and bang, break their pipe. And so water would be going everywhere, and we'd feel bad and be mad at the Scouts, And so water's spraying everywhere if you puncture the pipe. But what if you puncture the pipe and then you have a little tube going out of it? What happens is that the water level will enter the pipe and it'll go up and up until finally it'll reach an equilibrium and it will stop. And so a piezometer is a way of measuring the pressure by having the water level rise to a certain elevation that indicates the pressure in the center of the pipe. So if H is 10 meters, what would that tell you about the pressure at the center of the pipe? Well, you could just use the hydrostatic equation to find the pressure at the pipe, where delta P is delta H times the unit weight of the liquid. And if this is a water pipe, then the pressure in the pipe would be 10 meters times 9810, so it would be 98,100 pascals in the pipe if the water level rises 10 meters. So there's water pipes under most of the roads here in Huntington, but you don't see these big tubes sticking out of the road. So obviously it's not these piezometers that are being used in a practical sense to measure pressure, because number one, the heights involved would be really enormous. Typical water pressure for a water line in a municipal network is in the order of 500 kPa. So 500 kilopascals. That's a typical water pressure for a municipal network would be 500 kPa. That means 500,000 newtons per meter squared. So if we were going to use a piezometer to measure the pressure, like to make sure if maybe it was a little low or if the pressure was too high, how tall would that piezometer have to be to measure the pressure in a pipe where typically the pressure is 500,000? So to find the delta H that we'd expect, since we know delta P is delta H times gamma, delta H is delta P divided by gamma. And so it would be 500,000 Newton per meter squared divided by 9810 newtons per meter cubed. So that tells us it's going to be more than 50 feet. Anybody pop those numbers into your calculator and find out what exactly, no, 50 meters. Did I say 50 feet? 50.968 meters. So 50 meters, that's like half a football field, is how tall the pipe would have to be coming out of the ground in order to measure the water pressure with a piezometer. So this is one of the simplest ways to measure pressure in an enclosed conduit, but it's not very practical because the deflection involved is so enormous. And the other issue is that it's open to the atmosphere. You notice that it shows at the top of that pipe that it's open to the air, and so you could get any number of contaminants into your drinking water network if it was open to the atmosphere. So when we get together in class next time and start talking about manometers, more sophisticated manometers than this piezometer, we'll find a way around both of those disadvantages. Okay, we're going to talk about some key ideas in the homework. Just so you can, I'm trying to encourage you to get an early start on the homework. These are concepts that we covered in class today, and you can solve these problems right after class if you want. You could have them done before lab. So in this homework problem, you've got air in a pressurized tank. This is close to the atmosphere. So it's not atmospheric pressure air because it tells you that there's some gauge connected at A. So the air inside the tank is 50 kilopascals. And then at some elevation in the oil, they measure the pressure to be 58.53 in the oil layer. And they want to know a couple of things. In this example, they're asking you to find the specific gravity of the oil and then find the pressure at C. So remember, the definition of specific gravity is that it's a ratio of either densities or unit weights of some unknown fluid relative to the density or unit weight of water. So here they're asking what is the SG for the oil. And so what you can do is just apply the hydrostatic equation. One of the things I'll mention is that usually for gases, we don't bother keeping track of the pressure change when we're just going a small distance through a gas. Do you notice how they're measuring the pressure at the center line of the air tank? Well, the pressure here they're saying is 50 kPa. And what have I told you before about when you go down through a fluid, the pressure increases. But we're not bothering for something that has as small a unit weight as air, although technically what they're saying is that right here the pressure is 50 kPa. We're not going to find out how much different it is at the interface. And so anytime you've got a gas, unless it's hundreds and thousands of feet of elevation difference, that's when actually the pressure will change, is hundreds and thousands of feet. But for half a meter, not so much. So you can assume here that the pressure at the interface of the air and the oil is equal to the pressure that's read by that gauge. So the pressure here is going to be 50 kPa. And then how can you find the pressure here? Well, you're just going to apply the hydrostatic equation. The pressure increases as you go down. So remember, the way that we set it in one of the problems was P2 is P1 plus delta P. As you go down through the fluid, the pressure increases. If you go up through a fluid, pressure decreases. So if you know the pressure, though, if the pressure is known, what does the hydrostatic equation tell us about a change in pressure for some change in height and the unit weight? Any one of these can be the unknown. And here you know the delta P, you know the delta H, But what you don't know is the characteristics of the oil. At least initially, the unit weight of the oil is unknown. And so if you find the unit weight of the oil, then you can find the specific gravity of the oil. That's probably as much as I should give away about that problem. Any questions before we move on? All right, I hope this should look familiar. We did an example similar to this in class today. The only difference is that now here there is a deflection in the two cylinders. In fact, this problem's a little bit easier because you don't have to deal with the whole moment arm thing with the handle that's applying the force. They just tell you directly that you've got some force being applied at 1, how much can the force at 2 be? And the governing equations that dictates what that's going to be is that pressure is caused by some force exerted over an area. So they tell you the force, but they don't tell you the cross-sectional area. At least not directly. They've given you the diameter of that little plug that the force is being applied over. So you can calculate the cross-sectional area from the diameter that's given. Here's an important hint, is that not only in this course, but especially through the rest of your engineering career, you're going to have a lot more data than you actually need. You're going to get irrelevant information all the time. And clients especially are going to tell you all this irrelevant stuff, and they're going to think it's so important. And you're just going to have to filter through all the irrelevant things they tell you and find what does matter. And so, for example, when they say that it's 2.2 meters apart, that's irrelevant. But that's only one piece of irrelevant information, so they're not drowning you in it. I did a culvert analysis recently when someone's culvert failed because the water was rising really high during a storm and it was washing the soil around the culvert, and they thought for sure that the fact that the channel gets a little bit narrower 100 meters upstream was the reason why their culvert was failing. And I mean, you don't want to insult somebody who's paying you, but that wasn't had anything to do with what was causing the culvert failure. And so you're always going to have more information than you need when you're out on the job, and this is just your first taste of that, I guess, in terms of fluid mechanics. I'll put irrelevant information on quizzes and exams, and so just because it's given doesn't mean you need to know it. From the specific gravity, S here, by what they mean by S is the same thing as SG, specific gravity. So it's the ratio of the oil's density to water density, or it's the ratio of the unit weight of oil relative to water. So on this one, the pressure isn't going to be the same. The pressure here at that surface is not going to be same as the pressure there at that surface. The pressure at 2 will be lower than the pressure at 1. If this is 1, this surface, the pressure at 2 will be lower because as you go up through a fluid, pressure decreases. Any questions about this one? All right, last one. This is the weirdest of all. Okay, now we've got this weird device that it's like a container for water, air, and then some mystery liquid. It's more dense than water, so it's maybe some sort of a, I don't know what that would be, that would have a density of 3 times that of water, but some theoretical fluid, a liquid, that has a density 3 times greater than water. So what they're asking is, where is it inside of this that is going to have the highest gauge pressure? So that means relative to the open to the atmosphere, here the pressure is 0, but then when you go down through any liquid, the pressure is going higher. And then when you go up through a liquid, the pressure is decreasing. Now remember what I said about air is that you can go up through air, and as long as the elevation change is relatively small, you don't need to actually calculate the change in pressure. And that's true in this example. So you could go down some distance and find the pressure here, and they've given you the dimensions you need to do that, because remember they've got that 1 meter here, another meter, 2 meters, so you can find the pressure here, and the pressure of the water at this elevation is also going to be equal to the pressure of the air everywhere inside of here. And then it seems really strange, but the pressure there and the pressure here are the same, because they are in contact with each other through this air that has essentially such a minor pressure change vertically through the air that we assume the pressure here and here are equal. But then what happens as we go down? Is the pressure increasing or decreasing? It's increasing. It's getting higher. So have they given us the dimensions? Yes. They say that it's 2 meters to this imaginary line, then another meter. So you can find the pressure at the bottom here. You can find the pressure there. The pressure here and here is equal. I already told you that. You can find the pressure at the bottom there. And so the first thing they want to know is what is the pressure inside of this device that it's the highest. Where is the location of max pressure and what is that value? And then the other thing is they're wondering what is the force pushing up on CD. Now the width of this device is 1 meter wide, and maybe CD, line CD here, is some sort of like a gate. And they want to know how much they have to push down to keep that gate closed. And so it has an area of 1 meter, and so the pressure is going to be pushing up on that gate with some, the pressure, and the force is pressure times area. So that enables you to find out the force that's acting on surface CD. All right. We're not going to dismiss quite yet. I want to go through some information on the lab. And probably it'd be easiest if I just go grab the little device. I can bring it in here. So hang tight for just a second while I grab the equipment, and I'll be right back. Hi, how are you? They're doing well? Yeah, thank you. Sure, that'd be great. Yeah, that'd be nice. Yeah. Hi, son. Good. Okay. Here is the equipment that we're using today in lab.